Voici notre... here is our 10th candidate. It's Claire Paetsch. Oh, wow, you also have balls. Wow, that's a
full support
huge
system.
Fans, yes. Claire Paetsch, so your thesis is about modeling hydrogen-metal interactions from first principles.
That's correct.
Great, and it was done under the supervision of Professor Anirudh Natarajan.
Yes.
Are you ready, Claire?
Yes, I am.
Okay, have fun.
We are in the middle of an energy transition. We are relying more and more on the sun and the wind to power our world. But nature has its own rhythm, right? The sun doesn't always shine and the wind doesn't always blow. And the question becomes, how do we keep the energy flowing? My name is Claire and I study how hydrogen storage can help us solve this problem. Now, the tricky thing about storing hydrogen is its density. At normal condition, it's a gas, right? So it takes up a lot of space. The challenge is to store a large amount of hydrogen in a small volume and in a safe way. One promising way of doing this is to let hydrogen react with metals. Together, they form something we call metal hydrides. In the image behind me, you see hydrogen sitting in between the metal atoms. The colors mark different places that hydrogen can be in, each representing a unique neighborhood of metal atoms that surround it. But it's not that simple. Just like us, hydrogen can be a little picky. I try to have a conversation with them, but they won't tell me why they prefer bonding with some metals more than others. I mean, I get it. We're not on the same wavelength. We have to find another way. Now, we could try to test this experimentally, right? But there's simply too many metals to explore. And even then, hydrogen is hard to see. Turns out hydrogen is so light that it barely interacts with the tools we use to look inside materials. And that's where my PhD comes in. I built computational models that learn from quantum mechanics how hydrogen interacts with different kinds of metals. Once my models capture these interactions, I can run simulations at different temperature and pressure and predict how much hydrogen is being stored. And that's where things get really interesting, because these models can tell us something that experiments can't, and that is where the hydrogen prefers to be inside the metal. Turns out that most metals offer hydrogen one type of neighborhood. We found that the metals that tend to store the largest amount of hydrogen are the ones that offer multiple types of neighborhood. And that's what creates the extra storage. So with this insight in our models, we're able to explore more efficient ways of discovering better materials. Instead of looking for metals that squeeze hydrogen atoms closer, we look for metals that allow multiple types of places to be in. And storing more hydrogen means storing more energy. So when there's more sun and wind than we need, we can store this extra energy as hydrogen and turn it back into power when we need it most. And this all starts by designing materials at the atomic scale. Thank you.
Thank you. Thank you.